Hello there, welcome back to school. Here's a new video for you, and this video is going to be on the topic of electronegativity and bond polarity. So we spent some time in the first part of this unit talking about various periodic trends. We talked about um, effective nuclear charge, then ionization energy, um, atomic radius. And then we talked about electronegativity. Electronegativity is the really thing that we're going to take forward in the rest of this unit from the discussion of periodic trends. So if you'll recall from the previous set of slides, our definition of electronegativity is a tendency of an atom to attract electrons to itself in a covalent bond. And I've shown you a couple of these images before. I've added this H2 image here, but what these are called are electrostatic potential maps, as I mentioned when I showed these before. They are mapping the electron density in a molecule, and so the hotter it is, the more electron density it is, the colder it is, the lower the electron density. So you can see in this fluorine-fluorine bond, that is a fluorine molecule, there's an even distribution of electron density. And in a hydrogen molecule, H2, in which a hydrogen is bonded to hydrogen, there's an even distribution of electron density. But in the hydrogen fluoride molecule, which is what you get when you bond hydrogen to fluorine, you get a very polar bond. You get a molecule in which the fluorine side is very hot, lots of electron density, and the hydrogen side is very cold, very low electron density. And that's because although atoms will form covalent bonds by sharing electrons, they don't share those electrons equally. And you can see clearly when it comes to these two elements, hydrogen and fluorine, that fluorine is pulling a lot harder on the electrons that it is sharing with hydrogen than hydrogen is. Um, and so therefore the fluorine end of an HF molecule has a lot more electron density than the hydrogen end. We've seen periodic trends. We've talked about the periodic trends in electronegativity. Here's just an abbreviated periodic table, um, just reminding you what some of those electronegativity values are. And if I put in the little stair-step line that separates the metals from the non-metals, what is clear here is you can see that the metals all have very low electronegativities, and we know that metals tend to lose electrons. And nonmetals all have very relatively high electronegativities, and nonmetals tend to gain electrons. And then the metalloids along the stair step kind of have intermediate electronegativity values. Well, let's take a look at bonds and what happens when we bond elements together in covalent bonds and what happens with electron density and polarity when there are differences in electronegativity. So what this image shows is hydrogen bonded to the four common halogens. Hydrogen bonded to fluorine, hydrogen bonded to chlorine, hydrogen bonded to bromine, hydrogen bonded to iodine. And you can ignore this bond length and dipole moment column here, but what's interesting to see is just to look at the difference in electronegativity. And you can see that although these are all what we would call polar bonds, there's a spread of differences in electronegativity. The HF bond has a very large difference in electronegativity, 1.9. HCl is less, HBr is less, and HI is only a 0.4 difference in electronegativity. And that manifests itself in what you see here, where the electronegativity difference is very large. You can see that this is a very, very polarized bond. It's very blue, very cold over here on the hydrogen side, very hot on the fluorine side. HCl is somewhat similar as you get down toward HBr and then finally to HI, you can see that there's really sort of no blue color on hydrogen for HI and that the red and orange have really disappeared and it's just kind of yellowish color. And so while there is still a tendency of these electrons to be pulled toward iodine, this bond is much less polar. The HI bond is much less polar than the HF bond. And so we can use what we call binning, and binning is simply looking at a particular bond and looking at the difference in electronegativity between the two atoms, and then putting it into one of three bins, basically the bins being nonpolar covalent bond. And so anything that has an electronegativity difference less than zero point 0.4, we would consider to be a nonpolar bond. Anything that has an electronegativity difference between zero point 0.4 and about 1.7, we would consider that a polar covalent bond. And anything with an electronegativity difference of 1.8 or greater, we would simply consider that to be an ionic bond. Now, these are guidelines. I could think of one or two specific examples that don't fit these bins, but for the purpose of our class and our discussion, we're going to use these three bins and these numbers to classify things as polar covalent, non-polar covalent, and ionic. So we can try a problem. So here's a typical kind of problem you might see on a quiz or a homework assignment. Given these electronegativity values, which are just off of the table we were just looking at, which of these single covalent bonds is most polar? So if you'd like to turn the recording off and try this yourself and then turn it back on, you're welcome to do that. Well, the way you would approach this is by simply subtracting the smaller electronegativity value from the larger one in each case. So for A, that's going to be 2.5 minus 2.1, gives you 0.4. For B, that's going to be 3.0 minus 2.1, that gives you 0.9. For C, that's 3.5 minus 2.1, that gives you 1.4. For D, it's 3.5 minus 2.5, which gives you 1.0. And then finally for E, it's 3.5 minus 3.0, which gives you 0.5. And so the answer is C, the OH bond. They've set this problem up so that in each case, the more electronegative element is on the left-hand side. You might get a problem that's not like that. You're just always going to be subtracting the smaller value from the larger value. You'll notice that all these bonds fall into the category of polar covalent because they're all greater than 0.3 and less than 1.7. Some binning methods would say that the CH bond is nonpolar. Some binning methods go up to 0.4 as nonpolar. But again, for our class, we're going to say that that is a polar covalent bond. Okay, well, we can look at we can define a bond as being polar or nonpolar. We can look at the magnitude of its polarity. The one last thing we want to do is talk about what's called a dipole arrow, which allows us to actually indicate what direction a dipole is simply a permanent separation of charge, saying that one atom has a partial negative charge because it's more electronegative, and one atom has a partial positive charge because it's less electronegative. And so therefore, polar bonds don't just consist of a difference in electronegativity. There's a partially positive end and a partially negative end to every polar bond. And so what earlier we were looking at this image and saying that these bonds are all different because the electronegativity differences change, and therefore the bonds here, as we're going from left to right, become less polar. The one thing that these four bonds all have in common is that the hydrogen has a partial positive charge, and the halogen, be it fluorine, chlorine, bromine, or iodine here, has a partial negative charge. And that's because if we look at this table again, all of the halogens, fluorine, chlorine, bromine, and iodine, have larger electronegativity values than hydrogen, and therefore they're all going to be polarized such that the hydrogen end is partially positive and the halogen end is partially negative. And so we can use what's called a dipole arrow to indicate which side of a bond has a partial positive charge and which side of a bond has a partial negative charge. A dipole arrow looks like this, in which the crosshatched end on the left, it's on the left as I've drawn it here, is the positive end. That indicates the partially positive end of a polar bond. And the arrowhead sign indicates the partially negative end of a polar bond. The way to kind of remember which end is which is that the crosshatch sort of makes this look like a plus sign. So that's the partially positive end. The arrow is pointing in the direction that the electrons are being pulled. So that's the partially negative end. So we can try this on some bonds. We indicate the direction of the dipole, not the magnitude of the dipole, but the direction of the dipole by placing an arrow over the bond. And so here are 3 bonds that we can try this out on. So if we're looking at a CO bond, carbon has an electronegativity of 2.5, oxygen has an electronegativity of 3.5. So we draw the arrow in this direction with the partial positive end over carbon and the partially negative end over oxygen. This next bond, fluorine, is the more electronegative element, and so we would draw the dipole arrow in the opposite direction with the partially negative end over fluorine and the partially positive end over nitrogen. And finally, for a hydrogen-chlorine bond, which we actually saw in the electrostatic potential models earlier, hydrogen is less electronegative than chlorine, and so the bond dipole arrow is going to go in that direction. You may sometimes see, although and even from me, although I don't know that I'm ever really going to require you to do this, the use of of Greek delta signs to indicate bond polarity. That's simply saying that instead of using a bond dipole arrow like this, in which we put the whole arrow saying this is the partially positive end and this is the partially negative end, we could use these deltas to say this delta simply means partially positive carbon, partially negative oxygen. These 2 sets of symbols mean the same thing, and so these 2 symbolisms are saying the same thing, that this is a polar bond, that carbon is partially positive and oxygen is partially negative. We're generally going to use the arrows in this class. Okay, I think that is everything you need to have to complete the homework assignment that's associated with this video. So thanks for watching, and you may start in on your assignment.